when it is and if you take the tuning fork and it is set into vibration. So these are the few common examples which we come across. Now in linear motion it is very easy to find out the various physical parameters, but when it comes to the circular motion, the oscillations, we are supposed to be familiar with few of the parameters. So one by one we will discuss them. First we will see here a circular motion. Whenever a body is moving in a circular motion, suppose x is the initial point and it is moving a circular motion in this particular direction. Whenever it completes one complete rotation, it covers an angle 2 pi. Same thing here, that the graphical representation we have shown here, 2 pi. Suppose it starts from the point x and it moves to the point P. So how much it has displaced? It is not possible to find with the scale. So we are supposed to find out in terms of angle theta. Okay, the first definition is the displacement. What is the displacement? So it is nothing but it is the distance of the location of the body from its mean position in a linear oscillation motion. It means whenever the point is moving, as the point is moving, so its projection, if you take on the linear, that is y dash. So this x, suppose it has moved from x to p, if you draw the projection it will be at n. So this distance on, that is equal to x, it is nothing but the displacement. That's why it is from its mean position in a linear oscillatory motion. Or the other simple definition is the angle at which the body is located from its mean position in angular motion. Any one definition we can use. That is the displacement which has taken place. Now in the triangle ONP, the triangle ONP, this is the angle theta. So even this angle NPO will be also the theta. So in this triangle ONP, sin theta is equal to, this sin theta is equal to ON by OP, where ON is equal to x and OP is equal to this, the radius, we call it as A. Therefore A is equal to x into sin theta, or x is equal to A sin theta, but theta is equal to, from this equation we know that omega is equal to theta by t. So theta is equal to omega into t. Therefore we can write down the expression for the displacement is x is equal to a sin omega into t. Next, the another important parameter is amplitude. What is amplitude? It is given by the A. It is nothing but the maximum displacement from mean position. If you take the graphical approach, the maximum, this is a sinusoidal curve, the maximum displacement is here. The maximum displacement, this is the mean position, the maximum displacement from the mean position is denoted by A. This is nothing but the amplitude of the wave, and here also this is the maximum displacement from the mean position. This we are representing by A. Next comes the frequency. What is frequency? It is the number of oscillations per unit time, or number of oscillations per second. The unit is hertz. Means in 1 second how many number of oscillations such the oscillations does takes place, the complete oscillations. This is one complete oscillation from here to here, the 2 pi radians. Okay, so this is the frequency. Next comes angular frequency or angular velocity. What is the definition? It is the angle covered in unit time. Try to understand. It is the angle covered in unit time. So in the graphical representation we have shown here, that is omega. That angular frequency is omega is equal to theta by t. That is the angle covered theta in unit time t. So that is known as omega. Therefore, the simple definition is, it is the angle covered in unit time by representative point moving on a circle where motion is correlated to the motion of the oscillatory body. In simple words, we can make out it as, it is the angle covered in a unit time. Omega is equal to theta by t. Next comes time period t. What is the time period? It is the time taken by the body to complete one full oscillation. It means the moment we start the time here, it starts and comes here. It is one complete oscillation. Whatever the time is taken, that is known as the time period t, or here in the circular motion, it starts from x, go to y, x dash, y dash, and once again gets back to x. So whatever the time is taken to complete this one oscillation, complete rotation, is known as time period, and it is given by t. Then comes the equilibrium position. What is equilibrium position? It is the position of a body assumed at rest. Whenever the body is at rest, whatever that position, we call it as equilibrium position, or even it is a mean position of a oscillating body. Here you can see this particular line, it is the equilibrium position. So these are the few of the terminologies which are associated with the waves. Hope all you have gone through this relation in your PU1 and 2. The first one is the relation between nu, that is frequency, and time period t. The frequency and the time period. Suppose a body is executing n oscillations in t seconds. So n oscillations in the time t seconds. Therefore, frequency is, the definition of frequency is number of oscillations per second. Number of oscillation is n here, and time is t. Therefore, nu is equal to n by t. Call this as equation number 1. Also, time taken for n oscillations is equal to time t. That is, for n oscillations it takes time t. Therefore, the time taken for one oscillation is given by t is equal to t by n, small t by n. Inversing, we get 1 by t is equal to, now it is n by t. Call this as equation number 2. Now comparing equation 1 and 2, this equation and equation number 2. Therefore, we can write down nu is equal to 1 by t. So, frequency and time period, they are inversely proportional to each other. Similarly, one more the relation we want to establish, that is the relation between omega, that is angular frequency, and time period t. Let the body takes t second to complete one oscillation, that is time period is t, and it covers an angle 2 pi. Means for one complete rotation, it covers the distance of 2 pi. At that time, omega is equal to, the basic definition is omega is equal to theta by t. We know that omega is theta by t, that is equal to angle covered by time taken, that is angle covered is here 2 pi, and the time taken is t. We have mentioned here, and already we know that 1 by t is equal to nu. Therefore, it becomes omega is equal to 2 pi nu. So, this is the relation between the angular frequency and the time period. or even in terms of the frequency also we can establish the relation here. Next, these are all the things which we have come across. Now the next one is the restoring force and the force constant. So before getting into this, the restoring force, let us try to understand whenever a body is oscillating, what about its velocity, how its velocity is going to vary. Suppose we take a simple pendulum. This is the bob of the pendulum and it is set into oscillation. It goes to the extreme end and gets back and once again goes to the extreme end. This is how the simple pendulum is going to oscillate. So with respect to this one, so this is the mean position. It is connected to a rigid support. So this is the mean position or the equilibrium position. So these two are the extreme position whenever the simple pendulum, the bob is oscillating. Now, so with respect to this one, how the velocity is going to vary, that we are going to discuss, the 4 points. The first point is, here whenever a body is oscillating, its velocity, we are talking with respect to velocity, how this velocity is going to vary. The velocity varies as, the first one, it decreases when moving away from the equilibrium position. So this is the equilibrium position. Whenever it is moving to the extreme end, its velocity decreases when moving away from the equilibrium position. Second one is increases while approaching the equilibrium position. Same thing, when it is coming reverse, in the reverse direction, when it is coming from extreme to the equilibrium position, its velocity goes on increasing. Initially moving away, decreases, towards equilibrium position, velocity increases. The third one becomes maximum while crossing the equilibrium position. The velocity is maximum when it is crossing the equilibrium position, because from extreme end it is coming to the equilibrium position and it has to move away. While moving away, the velocity decreases. Therefore, it becomes maximum while crossing the equilibrium position. At equilibrium position, its velocity is maximum. The fourth point is, it becomes zero at the maximum displacement position. If you observe, when it goes to the extreme end, it halts for a while. In the sense, its velocity becomes zero. At extreme end, the velocity becomes zero. At the center position, it is maximum. So these are the 4 cases associated with respect to the velocity of the body in a when it is oscillating. Next comes the restoring force. What is the restoring force? The name itself indicates restoring. Okay. Now the definition is, it is the force whose magnitude is opposite direction to the displacement of a body with respect to mean position, and it leads to oscillations. Or it means whenever the simple pendulum, if you take, it is oscillating, at that time whenever it is moving from mean position towards the maximum, always there is a force, the opposition force. So that force we call it as restoring force. That restoring force, it keeps the body to get back to the equilibrium position. This is the force which is generated when the body is set into oscillation, such that it tried to get the body back to the equilibrium position. The name, that is the restoring. And mathematically it is given the restoring force. Suppose if F is the restoring force which is executing here, and X is the displacement which it has moved, and according to the definition of the restoring force, F here, it is the force whose magnitude F is opposite direction to the displacement, means F is equal to minus X. The restoring force is negative of the displacement X. If we equate, actually it should be F or we can f is proportional to, it should be minus x, or if it equate, it becomes f is equal to minus kx. K is the proportionality, so that proportionality we call it as the force constant. So f is equal to minus kx. It is one of the basic, the fundamental equation. F is equal to minus kx means restoring force, it always try to restore that into its original position. Now with this basic idea, now we will get into the simple harmonic motion, SHM. What is SHM? It is a periodic motion in which the acceleration of the body is directly proportional to its displacement from equilibrium position and is always directed towards the fixed point. Or in simple words, SHM is the oscillation where the restoring force is proportional to the negative of its displacement. Down f is equal to minus x definition. So that itself gives the definition for the simple harmonic motion. It is a oscillatory motion of a body where the restoring force F is proportional to the negative of the displacement. When if you remember this equation, easy to define the simple harmonic motion. Now this SHM we are going to express in terms of acceleration. In terms of the acceleration we are expressing. Now what are the characteristics of the simple harmonic motion? See, basically all the oscillations are not supposed to be simple harmonic. If that is the case, if it has to be a simple harmonic, so what are the characteristics of that simple harmonic motion? The first one is, it is a particular type of periodic motion. Yes, some periodic motion is there, means at a fixed interval of time that motion repeats. So it is going to be a periodic motion. Second is, the oscillating system must have inertia. So this is very important. It is going to have a inertia. When the inertia comes into existence, when there is a body of mass m is into account. Whenever a body of mass m is there, then inertia come into existence. Therefore, whenever a body is oscillating, inertia will be there. It is going to have a inertia. Third one is, there is a constant restoring force continuously acting on the body. As I said, in the simple pendulum case, whenever the body is moving away, a restoring force always it will be there. In simple harmonic motion also, the restoring force always exists. The fourth one is, the acceleration developed in the motion due to the restoring force is directly proportional to the displacement. Okay, here the acceleration, whatever the acceleration is developed during this SHM, it is that whatever the force is directly proportional to the displacement. The next one is, the direction of acceleration is opposite to that of displacement. F is proportional to minus x. They are opposite, in that is negative of minus x. Or we write F is equal to minus kx. What is F? F is equal to the force. We know that F is equal to m into a, mass into acceleration. The last is, SHM can be represented by a sine wave or a cosine wave. Okay, so which is given by x is equal to a sine omega t. Previously only the displacement we have come across this equation, x is equal to a sine omega t. So this is the simple equation which is going to represent a SHM. What are the examples of the simple harmonic motion? In the beginning only just I have highlighted about the simple type of the oscillation. Suppose a mass suspended to a spring, when pulled down and left free, execute simple harmonic motion. You take a spring for this spring, if you add the weight and pull it down and leave it, then what happens? This spring starts oscillating. So that type of the oscillation is nothing but it is a very good example for the simple harmonic motion. Second one is a pendulum set for oscillation. Previously we have seen the example, whenever we take the pendulum and we take it to the extreme end and leave it, it starts oscillating. So this is a very good example as far as the simple harmonic motion is concerned. The next is an excited tuning fork. So we have to take a tuning fork to one of its prong, we have to hit it against the rubber pad, then that particular the prong, it starts oscillating. So likewise a tuning fork is set into vibration. It is also a good example for the simple harmonic motion. The other examples are a plucked string in a musical instruments like veena, guitar, many more of the instruments, musical instruments are there, no? So the string based, so whenever we pluck or the string is set into vibration, the air molecules near surrounding that particular string, they are set into vibration. The next one is a shock absorber after being bumped. In almost all the vehicles, we are using the shock absorber. Whenever the humps or the bump comes, so we want to reduce the impact. So we use the shock absorber. Next, the swing with which the children play. In the garden, okay, we come across this one. Whenever in the swing they are oscillating, so that is also